So now we'll keep doing this. And then adding this additional constraint, and we solve the LP relaxation again, then we will get an answer, which will be the x1 is 6.5 and x2 is 3. So now x2 becomes integer, but now this is the problem. Now the 6.5 is the problem, right? Because this is not an integer. And then we find out the z is 34.5. So now I'm gonna branch out again based on this 6.5, right? Because the we already have x2 is an integer. So how can we divide it? I'm gonna add one more constraint. X1 should be less than equal to the 6. So again, we dividing from the 6.5. And then we add x1 should be greater than or equal to 7. Again, we are get rid of the reason, 6 point something reason. Okay. So, but still we are not losing any integer because I'm including 6 here. I'm including 7 here. So we are fine. And then we solve the LP relaxation again. And then we find out this is the not feasible, infeasible. Which means you cannot find out the solution because the original problems, you cannot have it because the 2x plus 4x2 should be less than 25, and then you cannot satisfy anything. So which means you ignore this branch. Your branch is done here. Now if you solve this LP problem, adding this constraint, which means from the original one, we already add x2 should be greater than 3, and then now we add another one, x1 should be less than 6. And then if we solve the LP relaxation problem, this one will be the x1 is a 6 and x2 is 3.25. Okay. Now we find out the z is optimal, the objective function, z is 34.25. And then we can keep going on because the lower bound is 34, but this is still the greater than 34. We can branch out more. Okay, I will branch out more here. And then since now x1 has becomes an integer, but now x2 becomes a non-integer again. So I'm dividing it here, but x2 should be smaller than equal to 3, or x2 should be greater than equal to 4. Again, we are not losing any integer values here. So we find out here solution x1 is 6, x2 equals 3, and we find out the z is 33. Now we don't have to divide it again, and then we discard this one because this 33 is smaller than 34, so we don't have to dig even more. So we terminate this node, and then we terminate here because it's infeasible. And then we look at this case. So this problem is from our original problem. We get rid of the integer constraint. We add this constraint. X2 should be greater than 3, and then x1 should be less than or equal to 6, and then we add x2 should be greater than or equal to 4, and then we got the solution if we solve it as a linear programming. Now again, x1 is not an integer value, but we don't have to branch out more because again our numbers 33.5 is lower than 34, which is the incumbent solution. So we terminate this node again also. So which means we terminate everywhere. So why I didn't branch out here? Because we already have a integer value. So if you branch out means you are adding more constraints. So it will getting worse and worse, right? Here we're getting worse, but because this is the LP relaxation solution, so we are trying to find out the real, our original LP problem. This is the incumbent, so we have only one incumbent. But while you are solving and you got another incumbent, which is better than this one, your incumbent solution change, right? And then your bound will change. So now we terminated all the branch. So we can conclude this solution is the real optimal solution. Okay, so we divide the problem, divided the area. So taking out the from 2.25 it's smaller than 2 or greater than 3. So of course we have to include the 2 and 3 so that we don't lose any feasible areas. And then we solve the LP relaxation. Again, we add the constraints, solve LP relaxation, and we find out this is the real optimal solution because we terminated all the area. All the case is smaller than this number, smaller than this number. This is not feasible. So this side, we cannot find out any better solution than the 34. So this is the real optimal solution. That's how Excel solver find out any integer programming problems.